Okay, this month we are looking at how to do just-in-time code generation using a library called ASmJit. And this is for just-in-time generation of assembly language. And we'll just briefly look at my use case. My use case is in this fractal renderer, Iterated Dynamics, there's a formula fractal type where you can write your own formula that is iterated over and over until some bailout criterion is reached. And there's initial conditions that are set up. And let's let you write your own fractal formula for an arbitrary set of equations that are iterated repeatedly to compute a fractal image, and it's got control structures, and there's a bunch of predefined variables, and there's a bunch of functions that you can call, and so on. So that's my motivating use case. And normally, what you want to do is you want to take some kind of input text, parse that into an abstract syntax tree, an AST. And in my situation, my code has an interpreter that interprets that AST, but the original code, the 16-bit DOS code, had a just-in-time code generator that was bespoke. It was written in assembly language and it generated assembly language. It would interpret the parsed structure for this formula type, and it would generate at the time x87, which is the floating point coprocessor for the 8086 was the 8087. So it would generate 8087 floating point coprocessor instructions to compute your formula from your text, from the formula that you had entered in as text. And when the code was ported to an entirely C-based implementation for the original Unix port back in the 90s, early 90s, the assembly language just-in-time code generator part was omitted since that was all written in assembly itself. And the intent was to port to other architectures like the Sun workstations, Spark workstations were current at the time, or a MIPS-based SGI workstation. Those are not using x86, so you can't run the x86 assembly language code that was implementing the just-in-time compiler. So instead, they just ended up with an interpreter. And that's where the code stands today. We haven't restored the functionality of the just-in-time code generator. So that's my motivating use case. And one option is certainly to use a full-blown compiler framework like LLVM. LLVM is a very heavyweight dependency. You can pick up LLVM through VcPkg, but it takes on my machine, which is not a slow machine. It's about a 1-year-old laptop, gaming laptop. It takes like an hour to build it, just to build the dependency. So that's extremely heavyweight. So I started looking around for other options, and that's why we have talked about the Highway library in previous meetings. That's a SIMD, a library for coding SIMD algorithms directly in C++, and it ends up calling the SIMD intrinsics functions, which invoke the SIMD instructions for your CPU. In the case of Highway, it acts as an abstraction layer between your actual CPU and the SIMD instruction extensions that you might have. So if you're running on ARM, it might, if you're running on ARM, the Highway library will choose the appropriate SIMD extension on ARM, and if you're running on x64, it'll choose the appropriate SIMD extension on x64. ASmJit is different in that you are literally writing processor-specific code. ASmJit supports 64-bit ARM and 64-bit and 32-bit x86. So x86 generally refers to the 32-bit instruction set. and x64 refers to the 64-bit instruction set. And there are differences between those two. And while we will talk a little bit about assembly programming in this talk, we won't go into the details of the entire x64 instruction set. I'll have the PDF up in a little bit, and you can see that just the instruction reference is 2,600 pages of PDF. So we don't have time to teach you about assembly language. There's plenty of videos on YouTube and web pages and tutorials and various places where you can learn assembly language. We will necessarily talk about some aspects of the assembly language that we're going to look at in the example code, but mostly we're going to talk about AsmJit. So if you go to asmjit.com, that's the home page for this library. There is complete documentation online. The documentation is very good. It's complete. It has examples, and it's kind of grouped into related functions are grouped into a single page. And if you look up here at the top of their website here, the support link, they have a Gitter channel. The author of this library hangs out on that Gitter channel and is usually available to answer questions. Obviously, I can't make any promises on his availability, but I had a couple of questions, and we had some discussions there about the library while I was implementing things. There's other people hanging out there as well, and discussions of, different approaches to solving a problem, because as you might imagine, there's many different ways to do the same thing in assembly language. So if you get stuck using the library, or the documentation has something that doesn't make sense to you or isn't clear, you can try that chat page. You will have to register to chat on there. I registered using my GitHub credentials, so that if you already have a GitHub account, that's an easy way to join that chat and discuss things. So, as stated, this little function guy is what we're after. So I need to parse your standard kind of math expressions. I implemented addition, subtraction, unary, minus, which is negate, right? So if I write minus minus 1, that's negating minus 1, which should give me 1. I didn't implement power. I did multiplication, division, addition, subtraction, parenthesized expressions, and parsing an identifier like Z or pixel as in my simple implementation, I just have that as a constant. Now, if we go over to my code, so I am picking up AsmJit as a dependency through VcPkg. I'm going to use the Boost parser library from Boost. This is a relatively recent parsing library that's been added to Boost. We've talked about Boost Spirit before. In fact, Spirit 2 was the very first presentation that I ever gave to Utah C++ programmers. That was about 10 years ago. And then more recently, we talked about Spirit X3, which was a successor to Spirit 2. And at this point, Boost Parser is considered more complete than Spirit X3. And it's considered, although it's not, doesn't share code lineage with Boost Spirit, it carries many of the same ideas for parsing. Boost Parser was created to make parsing Unicode text, or to better support parsing Unicode text than Boost Spirit was able to achieve, and overcome some of the deficiencies of Spirit X3 and Spirit 2. But it's very similar in design. It uses expression templates to represent the rules of your grammar. We'll look at that when we look at the code in a little bit. I'm using Google Test for my unit tests. And as we look at this code, you're going to see that unit testing is going to be an extremely important part of developing, firstly, developing anything with a parsing problem, because as your parser gets more and more complicated, it can get, um, you know, what's the word I'm looking for? It can get tricky, shall we say, to make sure that your abstract syntax tree that you're building up for your parser rules, as you build them up, to make sure that everything matches. Um, so let's take a look at the parser code first. So everything I've just got it all in one big source file. I've got a parse function, takes a string view and returns this abstract class that I call formula, and that has a way for you to set named constant values. You can evaluate the formula. Once the formula has been parsed, it's been parsed into a structure that's suitable for either for interpretation or for emitting code via JIT. If you just call this evaluate and you haven't called assemble or compile, then that is just going to be a plain interpretation of the abstract syntax tree. We'll see what that looks like. And there's kind of two ways of using AsmJit. You can either do using the assembler interface, or you can use the compiler interface. We'll look at both. They're similar, but the compiler is a little bit more abstract, gives you some additional facilities. But just to look at the parsing, this is this BP here. That's my alias for the boost parser namespace. So BP we're going to call parse. On the input text, expr is my rule for this lowercase expr. In fact, let me do this. Let me turn off Copilot completions so we don't get chatter coming up as I am navigating around here. Just by the way, I've been using GitHub Copilot both at work, and I have a personal license that I purchased, and it's pretty helpful in creating new code, learning new libraries. It's been a nice experience, so I give that a thumbs up there, just as an aside. Okay, so this expr is my rule for top-level expressions that are parsed by my AST. This BPWS is a white space skipper, so unless I explicitly tell the parsing framework otherwise, white space is allowed between any two elements of a grammar, an arbitrary amount of white space. This AST, this is the structure that is produced by the parse. For debugging, there's a way you can turn tracing on with Boost Parser. That's one of the areas where it got some improvement over Boost Spirit for parsing. If this parse was successful, then the value returned is implicitly convertible to a bool and will be true. My AST is represented as a smart pointer, so the parsing should have succeeded, and I should have got something non-empty from my AST. I've got an implementation of that abstract formula that I call parsed formula. This is standard, kind of hide things behind a pure virtual interface so that all your implementation details are hidden from clients. So this parsed formula derives from that abstract formula. And here we can see my parsing code. So up here, a few little helpers. This from Boost Parser, this char underscore says parse any character in the range of lowercase a to lowercase z. The vertical bar represents alternatives, so it can either, this alpha represents a parser that either parses a lowercase letter or an uppercase letter. And then digit here represents a parser that parses a single digit. And then my alphanumeric constraint here is it's either a letter or it's a digit or it is an underscore, so that my identifiers it has to begin with a letter, and then it's 0 or more alphanumeric characters after that. So you can go back and look at my video on Spirit X3 to kind of see a lot of the details of how this works, but we're using what's called a domain-specific language, which is, the fact that I'm building these parser constructs by using C++ operators like OR and greater. This lexeme thing, basically for this selected stuff, it suppresses the white space skipping, so that means that my identifiers, its letters followed by 0 or more letters, numbers, or underscores, and there can't be any spaces between those individual pieces of the identifier. I've got some rules down here, and each rule in Boost Parser, you have a little tag type that's just used to discriminate the rules. These are just a declaration of a name, basically, as a type, but there's no, that's struct number tag. There's no definition for struct number tag. It's just, again, just a name for a type that's used to discriminate these rules. The second template argument is the synthesized, well, let's just say it's the attribute for the rule. Boost Parser can synthesize an attribute for you, or you can make your own type for the attribute, and that's what I'm doing. Is I'm basically saying all these things turn into this expert type, which, as you see up here, is a shared pointer to something called a node. So I'm going to build a tree of nodes, and each of my parsing rules is going to generate nodes that get connected together into the tree. So a number, this annotation here, you can take a parser and then apply a semantic action to it by putting the semantic action in square brackets after the parser. So I'm going to parse a double, and then I'm going to turn that into a number node. I'm going to parse an identifier. I'm going to turn that into an identifier node. I'm going to parse unary operator plus or minus followed by a factor, whatever factor turns out to be. I'm going to turn that into a unary operator node. And then down here, I'm going to take either a single factor or a factor followed by one or more multiplicative operators, so star and slash, followed by another factor. I'm going to turn that into a sequence of binary operators. And similarly for term, I'm going to take a term and then it's going to be followed by 0 or more sequences of additive operators, plus and minus, followed by another term, and I'm going to convert that into a binary operator sequence. So you might say, like, well, star and slash and plus and minus, why do you have different rules for that? Why don't you just combine it all into a binary, a single make binary sequence? And the reason that you do this is you see that an expert expands into a term expands into a factor expands possibly into a parenthesized expert or some other thing. And the reason you split these rules out this way and make them kind of mutually recursive is so that you essentially implement the precedence of the operators by how you define these rules. So the defining the plus first gives plus like the lower precedence compared to multiply and divide. Plus add and subtract have a lower precedence compared to multiply and divide, which is what you want. For most C-like languages, multiply and divide have a tighter precedence than add and subtract. Okay, so just the mechanics of defining a rule with Boost Parser is you have a thing, a name, and that name, oops, I'm always doing that with my keys here. The name underscore def is the thing that expresses the definition of the rule in terms of its parsing. And then up here is the name declared as a boost parser rule that expresses the attribute type associated with that rule. And then this macro here glues the three things together. It glues together the rule declaration and the rule definition and the attribute type. It glues them all together. And all that means is that in the end, I get this expr rule that I can use as my parser down here. So this expr refers to this rule. And the only other thing that for the parsing is these little semantic action functions. They take the parsing context, they extract attributes out of the parsing context, and use them as arguments to a constructor for the particular node type. And if we look at my node stuff here, so I have a virtual base class for an abstract node, and on each node is going to implement a method for evaluating the AST as an interpreter, or invoking the AsmJit assembler to assemble code, or the AsmJit compiler to emit assembled code using a slightly higher abstraction. And we'll see what that looks like in a second. So these parsing rules were associated with these little semantic actions, these little helper functions, that what they do is the built-in attribute for boost parser. So every parser that you write in boost parser has what's called a synthesized attribute. Or that attribute may be none if it's like just parsing literal text and doesn't produce a value. And because I've expressed my rule attribute as a shared pointer to a node, boost parser itself doesn't know how to construct a shared pointer to my different node types. So I write these little semantic action functions as lambdas. They take the parser context, so they're taking it as auto, so it's a generic lambda. Take the parser context, get whatever out of the parser context that they need in order to invoke via std_make_shared the constructor for the different node types. So number node is really simple. It just constructs from a value and then stores that value inside there. And if we're going to evaluate a number, it just returns the number, right? That's fairly straightforward. So if we go up here to node and we see who implements evaluate with Alt-End in ReSharper, we can see what does the evaluate do for when it's an identifier. Well, my evaluate method takes a symbol table as an argument, so this identifier node knows the name of the identifier that was parsed out of the text. It looks it up in the symbol table, and if it's present in the symbol table, it returns the associated value in the symbol table. This symbol table, by the way, is just a type alias for a std map from string to double. So it looks it up in that map. If it found it in the map, it returns the value from the map. Otherwise, it returns a value of 0. If we go and look at, let's go back here with Alt-Home to get to the base method, and then we do Alt-End to look at who's implementing the derived classes. If you look at binary op node, it's going to evaluate the left-hand side of the binary operation, whatever the expression was on the left-hand side of the operator. Then it's going to evaluate whatever was on the right-hand side of the operator. Then based on the operator, it's going to return the appropriate interpreted result. Now, when I parsed, even though I had different rules for a multiplicative binary operator, and I had a different rule for an additive binary operator in my abstract syntax tree, they're the same node. There's a left side, there's an operator, and there's a right side. So this interpreter just does the obvious thing based on what operator it is, and so on. Similarly for got unary operator node. If it's unary plus, we just return whatever the operand was, the evaluated operand, because if I write +1 or +-1, so -1 gets parsed as a number, and then the plus gets interpreted as a unary plus on the value -1. Well, it's just -1, whatever that expression turns out to be. If it's unary minus, then we have to take the negative of whatever the evaluated expression was. So the only other one we haven't looked at was we did look, okay, so we looked at identifier. I think we've looked at everybody now. So the binary op, the identifier, a number, and unary op. Now, when we're emitting assembly code in a JIT fashion, we do the same kind of thing that the interpreter does. I found it useful to, if you look at our tests over here, I just have all the tests in a single file. I found it easiest to start out by just saying, this text should successfully parse. I don't care what the abstract syntax tree is or whatever. I'm just testing my ability to parse and recognize valid constructs in the source text. So I have a bunch of tests for parsing, and then I start writing tests for evaluating what was parsed. So I'm asserting that if I parse the number 1 and then evaluate that, I better get 1.0 back. Technically speaking, you might want to make this like assert near and then say like 1 e minus 6, because comparing floating point values for equality can get you a fragile test, which is why Google test has this assert near macro instead of the assert equal. For these tests, I think it turns out that the values that I'm using, 1 and 2, can be exactly represented in floating point. So, I don't feel bad about comparing them for equality, but just something to be aware of when you're writing tests around code that produces floating point values. You'll see that in some of these tests I do use assert near or expect near instead of assert EQ or expect EQ in order to account for possible inexactness in floating point representation compared to the number that you write down. It's possible to write a floating point constant as a decimal number that can't be exactly represented as a binary number. So just something to be aware of when you're dealing with floating point values. But that's just a side digression. So I found it useful to, I'm just testing. First I tested my parsing. Now I'm testing my interpreter. And the interpreter is validating. I'm not only validating the code that I wrote that interprets the AST, I'm implicitly validating the AST without doing a direct probe into the AST itself. The AST is an implementation detail. I know that if the AST generated for 1 + 1, when I evaluate that, it better come back 2 or I got a problem. How the AST represents 1 + 1 is not important to me. What is important is that when I traverse that AST and evaluate the result, that I get 2 for 1 + 1. So similar, I have a bunch of different evaluate tests here that just go on. And it's where it starts to get interesting is when I start testing an assembled formula. So I'm going in my setup for my test, I parse it into some internal representation. This result of parse is a smart pointer to an abstract formula. So I'm just asserting true that the smart pointer came back non-empty, and then I'm going to call assemble on the formula that returns a Boolean value. So I'm just asserting that the assemble was correct. And then I'm going to call evaluate again and assert that I get the right value out. The difference here, if we do, let's try it this way. If I go F12 over to here, it's being stupid. It's taking me to the wrong evaluate. Oops. Let's close this. Get out of the end here. I know where it is. So here's my implementation of the abstract formula for the evaluate method. I've got a function pointer here. And if that function pointer is non-null, then I'm just going to call through that function pointer. Otherwise, I'm going to call evaluate on the AST with some state that it needs to perform the evaluation, namely the symbol table state. If I've taken my formula, parsed it, and then I called assemble on it, then this function pointer will be non-zero. So let's just go back over here to their documentation. So the top level of their docs describes the different groups of documentation that they have. And basically the place to start is with the core. Now the core describes two things that you're going to need in order to generate code. There's a code holder that is a class that basically is a buffer that's used at code generation time. And then there's a target, and they only have, although this target is represented here as an abstraction, they have only one implementation, this JitRuntime. And the JitRuntime class is the thing that will hold the final version of the generated code. And I say the final version because if you've ever used an assembler directly by writing assembly code and passing it off to an assembler program, you'll often see assemblers describe themselves as a one-pass assembler or a two-pass assembler. Sometimes, if you look at very old assemblers, they might even describe themselves as a three-pass assembler. And what that's referring to is, for instance, in a two-pass assembler, the first pass might be walking over all the code, identifying all the labels, which represent symbolic names for addresses in the generated code, and collecting all the labels together and identifying the labels that the names that have to be resolved to actual locations on the second pass. And then on the second pass, they might generate the actual code substituting the values of the labels that they encountered on the first pass. Exactly what happens in the different passes is described for each compiler, but you can kind of think of the code holder as the place where the results of the first pass take place, and then the JIT runtime as the result of any second pass that may need to have been applied. And we'll see how that kind of second pass can come up in the API here. The lifetime of this JIT runtime must exceed any function pointers that you get from code generation. So the basic process is you either use some kind of emitter to emit code into a code holder. That's your just-in-time code generation. And then the result is going to be associated with this JIT runtime object. So if we go back to our code here, my parsed formula, I have the JIT runtime. I have a logger to standard out that I'm using to see what kind of code is being emitted. This isn't strictly necessary, but it's very useful in understanding what's actually happening with the assembly code that you're emitting. We'll see what that looks like when we run the program interactively. This is my function pointer that I'm going to get as a result of either my assemble operation or my compile operation. And so I'm holding the function pointer and this JitRuntime as members of the same class, so they have the same lifetime. So it's not possible for me to call the function with the runtime having been destroyed. If you do that, it'll just segfault, so that's bad. Don't do that. I've got my AST held inside from my, this is my parsed formula class. So I've got the result of my parse, and I've also got this thing that I'm calling emitter state. And this is a state that I'm going to need for either calling the assembler style of code generation or the compiler style of code generation. So I've got a symbol table. This is just a map of string to double. I've got a data section where I'm going to use a chunk of memory for storage of constants. And those constants can either just be numbers that were parsed, or they can be the named values from my symbol table that were referenced in the text input. So we have to talk a little bit about how you write assembly code that you can call from C or C++. So let's get back over here. And the different operating systems and different compilers have different calling conventions. And the calling convention is just a name for where do the inputs to a function go. And when I say where do they go, I'm talking about the CPU, which CPU registers or are used for input arguments. How is the return value from a function returned? And there's a, for instance, for x86, there's a 32-bit calling convention and there's a 64-bit calling convention. Now I'm doing 64-bit code here. I didn't do any runtime checks for 64-bit code. I'm just assuming 64-bit code in my use of ASMJit. But there is a way that you can adjust your code for either 32-bit code generation with ASMJit or 64-bit code generation. We'll look at an example in a second that takes care of that. In my case, I'm implementing a function that takes no arguments and it returns a double. So the calling convention is that floating point return values from a function are returned in the XMM0 register. Now, we've talked about SIMD instruction extensions for x64, SSE2, SSE3, and so on. We talked about those before when we talked about SIMD libraries. It turns out that although there is still the floating point unit coprocessor in a modern x64 machine, the so-called FPU, which originally was the 8087 and so on, 8287, 8387, and then with the 486 it was integrated onto the CPU chip, and then it was the 486DX specifically, I believe, that the floating point unit was on chip and could always be assumed to be present. However, that's basically considered a legacy path at this point. And instead, what you do is you use the SIMD registers. This XMM0 is a SIMD register. Use the SIMD registers, but you just use the SIMD instruction variants that treat the entire register as holding just a single scalar value. This is all covered in detail in the Intel manuals for the instruction set for 64-bit and 32-bit architectures. You notice that this manual, this is the complete A to Z reference. I don't know if you can see this, but it's 2,605 pages long when it's all combined as a single volume. So if you go to the Intel website to download these things, they have the individual 2A, 2B, 2C, and 2D PDFs that you can download. I just like to have it all in one PDF so I don't have to bounce back and forth between different PDFs to look at the different instructions. And so really to do any kind of reasonable amount of assembly language just-in-time code emission, you're gonna need to refer to this manual, and you're gonna need to refer to it frequently. I'm not going to go into a lot of the detail of what I'm doing other than describe like my algorithm of how I'm doing it, but I had to refer to this manual in order to find the right instructions to do the right thing. Now, because the floating point value from a function has to be returned in the XMM0 register, I end up looking at things like, say to do addition, I have to go to A. Okay, so add scalar double precision floating point values. This uses it's an instruction from the SSE2, and then later AVX and AVX 512 or AVX 10. But this annotation here is saying the mnemonic is add scalar double. That's how you read this. And the first argument is the destination, and that is an XMM register. And then the second argument is either another XMM register or it's a 64-bit memory location. So when I interpret a binary operator node that's doing addition, I need to emit this instruction. So before you can use AsmJit to get the work done, you have to know what instructions you're going to be using, and you have to understand their arguments and the valid constraints on what those arguments can be. In Intel assembly syntax, the destination register is shown first and the source register is shown second. And if there's more than one source operand, the source operands come second. And this description here says, add the low double precision floating point value from XMM2 or memory to XMM1 and store the result in XMM1. So it's really equivalent to if we were to write this in C++, if we write a notepad here, you can think of it as XMM1 plus equals XMM2. This is what it implements in a single instruction. So let's go back and look at an example. Before we look at the details of how I'm emitting code in my assemble and compile passes, let's look at an example I copied straight from their documentation so we can just get a general overview of how these classes work inside AsmJit. So in this case, they're going to implement a function. So this is a type def for a function that returns an int. It takes a pointer to a constant integer, and it takes a size t count. And you can kind of tell from the name SumFunc that what it's going to do is sum up count elements from this array of integers and then return the sum as the return value. So we need a JitRuntime. We need a code holder as a place to build our code. You set up the code holder from the runtime environment and the CPU features of the runtime. If you want to restrict your code generation to specific CPU subsets, you can do that by specifying the CPU features yourself instead of obtaining the complete set of CPU features from the runtime. Basically, this JitRuntime, when you create it, it's going to end up calling the CPU ID instruction to identify what the instruction set capabilities are of the machine you're running on. And then we're going to build an assembler class. This is the thing that's going to have methods on it to emit code into the code holder. And then here I mentioned that there's a way to to detect if you're targeting a 64-bit architecture or 32-bit architecture. And he's going to check to see if we're on Windows, because the calling convention for the first and second arguments in terms of MSVC, the application binary interface, it's different than GCC. So I mentioned that calling convention stuff, it's dependent on not only the platform you run on, but it's dependent on the compiler that you use. So different compilers pack the arguments to functions and interpret the return values of functions in different ways. It turns out that for both Windows and non-Windows, the return value is going to be in the EAX register, and the input arguments are going to be different depending on if it's Windows or not. Now, what they've got, what the abstraction that they provided here is that this GP member of the x86 namespace, so this x86 namespace is inside the AsmJit namespace. He's got a using up here that brings the entire AsmJit namespace contents into view, so that's why this JitRuntime didn't need to be qualified, this cold holder didn't need to be qualified, and so on. But anything pulled out of the specific instruction set architecture is in a nested namespace. So there's x86 for the Intel architectures of x86 and x64. And then for the ARM architectures, there's a different nested namespace. But each of those namespaces has an assembler class, and within those namespaces, you can reference the names of registers. And there's this thing called GP, which stands for general purpose. So this is a class that represents a register, a general purpose register for x86. And these GP values, they're not they don't have polymorphic behavior, so you can treat them as simple value types. They can be copied around, they can be mem copied. You can just think of them as a struct with some fields in it. There's no polymorphic behavior there that you need to worry about. So no virtual functions. They're plain old data values that you can just copy around. And it's just recommended that you pass them by value if you have to pass them anywhere to any of your own functions. So you don't need to worry about them being heavy to copy or anything like that. So this is handling 64-bit ABI, Windows and non-Windows, or 32-bit ABI. And you'll see here that in order to emit assembly language using the assembler, you just call methods. If we drill into this method definition, you can see here it's ASMJit instruction 2x, which means it takes two operands. And if we look at that macro, it expands out into a thing that declares a function that returns an error code. And it basically says, take my emitter and emit this instruction with these two operands. So we're going to emit a move instruction that says, move into this argument. So the destination is always first in Intel style. And what we're doing here is ESP is the stack pointer. So we're going to build a pointer to the stack with an offset of 4. This is 32-bit code, so the pointer to the array will be on the stack, and it'll be 4 bytes down because it's a 32-bit code, so the pointer is 4 bytes wide, not 8. And then the next 4 bytes down will be the count. So we're going to generate a move instruction to move into the count register from the stack, 8 bytes down, a 4-byte quantity. Then we're going to, because we're going to do a summing loop, we're going to need some labels. And from the assembler, you can call new label to get a label. If you want the label will be generated in the assembly output with a kind of an auto-generated name. If you want the label to have a specific name, we'll see how to do that when we look at my example. So we got a couple labels here. The loop label is because as you're summing up the array, you need to keep looping over the elements of the array, so you need to go back to sum up another value, so that's this loop. And then when we're done, we're going to branch to the exit to get out of the loop. That's the other label. This XOR trick is, if you say A equals A XOR A, it ends up writing a 0 into A. Now, you could also do a move with an immediate value, and if some of this stuff doesn't make sense, like what's an immediate value versus why are we doing this XOR thing, again, details are going to be in that 2,600-page document describing the instruction set, and that's just for Intel x86 and x64. If you want to also have a code branch where you're emitting ARM64 code, you're going to have to go and download the instruction set manual for ARM64 and learn the ARM instruction set, and it's going to be different. It's not going to have these methods necessarily called XOR or whatever. Just as a side comment, the reason this XOR has a trailing underscore is because you may not realize that in C++ there are text names for the operators, like circumflex is the XOR operator, but there's also, you can write A XOR B. Notice it colored it blue as a keyword. So that's why this has to be XOR underscore instead of just XOR, because XOR is a reserved word. So just be aware of that. If you see some of these things with the trailing underscore, that's why that is there. Otherwise, if it's not a reserved word, he's just using the name of the operand as the name of the method on the assembler class. So he's doing an XOR. Again, this is a trick just to get the register to be 0. Doing a test, and then testing the count. If the count is 0, we're going to branch to, so JZ is jump if 0. If that count register is 0, we'll jump to the exit label. Otherwise, we're going to bind the loop label to the current location in the assembler. So this is going to be the top of our loop that is repeated. And this initial jump is just like, hey, you told me to count up 0 integers, so we're just going to leave straight away having set the sum to 0. So here's our loop that is bound to the current instruction location in our code holder. We're going to do an add. We're going to add the so this square bracket notation is what you would see if you were writing assembly code directly. In JIT you construct a pointer. This is a strongly typed thing, so that when we invoke the add method, you notice it goes to the variation of add that takes a general purpose register and a memory location. Notice there's another variation up here that says you're adding one general purpose register to another general purpose register. So when we call x86 dword pointer with this register name, it says we're going to load indirectly through the register. So the register is not the value, the register contains the address of the value. Again, this is just kind of assembly language programming. It's very, very low level. You got to think about addressing modes and so on. The way JIT handles that is everything is done through strongly typed overloads, and the variant of the instruction that is selected is based on the types of the arguments that you pass to the method on the assembler class. So down here, we're calling add again, but this time there's a constant being passed, and we're saying add 4 to this ARR register. So if we drill into that one, you see that the variant of the add instruction is The first operand is a general purpose register, and the second operand is a so-called immediate value. And if we drill into this IMM, we see that it is a thing that is, if we go down here to the value, we see here that it is a thing that is constructible from a t value, and there's a little bit of template magic to make sure that we're calling this overload in the right circumstances. Here's another overload where the immediate value is a float, and here's where the immediate value is a double. So that's how AsmJit is generating the different instruction variants with what looks like a single method. In reality, it's overloads of a single method, and the overload is selected based on how you construct the arguments to the method. So in this case, the add was adding to a general purpose register from a memory location, the value stored in a memory location. And here, we're adding to a general purpose register from an immediate value, a so-called, it's called an immediate value because this value 4 is encoded directly into the machine code. It's not loaded from some arbitrary location in memory. It's part of the instruction stream. So hence, the value appears immediately as part of the instruction. We're going to decrement the count register. This decrement operation, and pretty much any math operation, will set the flags register in the CPU so that we can say jump if the 0 flag is not set, so jump non-zero, back to that loop. Now, we didn't specify the exact values of these labels. Here we bound a label to the current instruction pointer. And here we are referencing that location by using the label. You see here the jump is taking a label type as the argument to the method. And then here is our other label that we're going to bind at the end, right before you return from the function. And again, according to the ABI, we're going to return for integer functions. If we go back and look at that thing that came up through the search, integer functions return the value in the EAX register. So that's what we did, is we made sure that when we got here to the return instruction, that the EAX register contained the sum that we computed. So at this point, we're done with this assembler class. The assembler class is basically just used as a helper to generate the necessary bytes into the code holder. So really, right here, we could put this whole thing inside a scope with curly braces, and everything would still be fine. Might be a useful way to express that in the example, instead of a comment saying, that this assembler instance is no longer needed. If we put it inside a scope pair of braces, that would make it explicitly clear that the assembler class is no longer used after that. So we used the assembler. We generated a bunch of instructions into that code holder. Now we need to get a function out of it. We do that by asking the runtime to add a function. We give it the address of our function pointer, and we give it the address of the code holder that we used to hold the instructions that we generated with the assembler. Just do a little error checking here, and then now we've got a pointer to this function, and this function is of the type takes a pointer to an int array, a const int array, and takes a count and returns an int. So we can call that function with a pointer to a const array, const int, a pointer to an array of const integers, and a count. and get the result back. And so if we run this little example, set it as a startup project, and let's just undo whatever little edits I was doing. And if we run this, it builds it, and it says the result is 108. Now, that's all nice and dandy. Once you're done, if you're done with the function, you can explicitly remove it from the runtime. This code is obviously going to exit right here, and the runtime would be destroyed anyway. But you can, in the same way that you tell the runtime you are adding a function, that function stays alive until you release it or until the runtime itself is destroyed. Now, if you know anything about modern CPUs, you know that they have a dislike for quote-unquote self-modifying code where people just scribbled some arbitrary code into a memory buffer and then call into it. And that's a essential security hole. That's how all these stack overflow security and vulnerabilities work, is they try to scribble some stuff into a buffer and get the computer to treat that buffer as executable code and invoke code that they scribbled into that buffer. So the JIT runtime is responsible for orchestrating a conversation with your operating system to make sure that the code that you've generated as machine code bytes into a buffer is suitably annotated so that you can execute that code. As a consequence, this JIT runtime guy, this guy, it can be expensive to create and destroy these, so you probably want to keep this around for the lifetime of your program or the lifetime of any. Obviously, it needs to be kept around for the lifetime of any JIT generated code. But what you don't want to do is create the runtime, JIT some code into the code holder, get a function for that code, call the function, and then destroy it all, and then do that all again the next time you need to do things. You want to treat this guy as a heavyweight class and have it live around for as long as you need to do JIT type things. Now, if you're in this code, it's straight line, generate some code, call it once, and then exit. So, it's going to destroy this guy every single time you run it. But if you were doing some kind of interactive loop, say you were obtaining these data values interactively, or you were, processing a bunch of files, you want to, have that happen and keep that function alive for as long as you were processing data and keep the JIT runtime alive. Obviously, it has to stay alive. The lifetime of the runtime has to exceed any of the function pointers that you got from the runtime. So that's example straight from their docs. It just shows all these things coordinated together. Now let's go back and take a look at what I'm doing. So I've got each of these nodes, and here's my node class. And each of my nodes has specialized this assemble method. So if we look at, for instance, what am I doing with a number? Well, I am doing something a little bit fancier. I am going to take any of these constants that I am referencing, and I'm going to store them in a data segment and get a label that refers to the address of the constant. And then in my case, my constants are floating point values. So I am doing, and more importantly, they're 64-bit floating point values. 64-bit quantities in x86 are referred to as quad words. So you have a byte, that's 8 bits, and you have a word, is 16 bits. You have a double word, which if you ever wondered where that D word terminology comes from, a double word is 32 bits, and then a quad word is 64 bits. So I'm using move Q, which moves a quad word quantity, so a 64-bit quantity, from the pointer associated with this label. So that label represents a location in memory. I'm going to use that location in memory as a pointer. So I'm not loading the value of the label, I'm loading the value pointed to by the label into the XMM0 register. And if all I need to do is emit assembly code to evaluate a constant, then I'm done, right? Because my return value is going to be an XMM0, and in terms of generating the necessary assembly to represent a constant, all I need to know is where that constant is in memory and then move it into XMM0, and then we're done. In terms of the big picture, my formula implementation, as I mentioned, we've got to keep this JIT runtime around, so it's got the JIT runtime as a member in my formula implementation. And when I ask a formula to assemble itself, I need to, I'm going to need a code holder. I'm going to initialize that up, and then I'm going to need an assembler, and then I'm going to recursively invoke assemble on the nodes in my AST. And by doing the recursive invocation of my AST, I end up with the right order of operations in the assembly code corresponding to the structure of my AST. And, my AST allows arbitrary number of plus, additive terms and arbitrary number of multiplicative terms. And I can change the operator precedence by putting parentheses around things. So I structured my AST in such a way that essentially a depth first recursion on my AST gets things evaluated in the right order. If this may fail for whatever reason, so it's just a little error checking here. The very last thing in my assembly code is going to be the return function that returns from the called function that I've generated. I'm going to emit a data section that holds all my constants. We'll see what that looks like in a second. I call the runtime to get my function pointer. That may fail, in which case this error value will be non-zero. If for whatever reason the function pointer I got back was null, then that's also an error. Otherwise, I return true to indicate that I successfully I successfully generated assembly code, and I have this function pointer that represents the assembly code. And if that function pointer is non-zero, when I call evaluate, it's going to call that function rather than my interpreter. Might have been a little better for me to structure this so that I had like an interpret function and an evaluate function, and the interpret function always called the interpreter on the AST, and the evaluate function always called the compiled output. I had a little bug in there where I was writing this code and my assembly code was all bogus, and I couldn't understand why my tests were passing, and it's because this function pointer was always null, so I was never actually calling the function that I thought I had generated because I didn't generate it correctly. So let's take a look at the different, not every single one, I don't think we need to take a look, but let's look at like binary op node because that's kind of the most complicated one. So if you remember, a binary operator node has a left-hand side and a right-hand side and an operator. So I'm going to recursively descend on the left-hand side and do the assembly. Now, when that comes back, the result of whatever that left-hand side will be in XMM0. But if I call assemble on the right-hand side immediately, it's going to overwrite this value of XMM0 with whatever was computed for the right-hand side. So I need to save that off. So, and the easiest way to save things is to use the stack. Now, it turns out you can't take the XMM0 register and push it onto the stack directly, just as the 64-bit quantity. You can push the whole an XMM0 register is actually 128 bits wide. It's got a space for two 64-bit doubles. I just want the one double on the stack. So if I do this move queue from XMM0 to RAX, general purpose register AX. Then I can get the low 64 bits out of the 128-bit register, and then I can push that 64 bits onto the stack. I can then assemble the right-hand side. I can stash off the result of that right-hand side from XMM0. I can move that into XMM1. Then I can pop from the stack into RAX, and then I can move from RAX into XMM0. So now I have the evaluated result of the left-hand side in XMM0, and I have the right-hand side in XMM1, so I can issue a single instruction depending on the operation that combines XMM0 and XMM1. Remember these instructions, it's XMM0 gets XMM0 plus XMM1. And for plus, it doesn't matter in which order you add them, but when you do subtract, you have to make sure that you subtract them in the proper order. So again, just doing, it's either add scalar double or subtract scalar double, multiply scalar double, or divide scalar double. And there is, if we go to base class and look at the derived classes, similar classes for the other nodes. The binary op one is the most complicated one. So if we look at where this is called, so we are recursively assembling the AST into the code holder using, this assembler is attached to the code holder. So we just need the assembler itself, and we're calling methods on the assembler to emit code into the code holder. We emit our return instruction. And then the last thing we do is to generate the data section. Now, in assembly language terms, sections are just chunks of memory, and it's convention to call the section holding data the .data section. And if we go back here, init code holder, what I was doing here is I was doing that init method to associate it with the runtime. I'm setting my logger, and I'm also creating this data section by calling code.newSection. And so when I get down, let's get down here. When I get down to the end of assemble and I emit the data section, I'm going to tell the code emitter, which in this case is the assembler, I'm going to tell this emitter to switch to the data section, and for each of my named constants, I'm going to bind the label associated with that named constant and emit the double into, can emit the bytes that represent the double, the value associated with that name into memory. And then down here are the constants that didn't have a name, so they're just in line like 1.0 or 6.02, whatever. I'm going to bind the label to whatever the address is in the data section at the time and emit the double value for that constant. And the way my code works here is that anytime I need to get a label for a constant, so this is not a named constant, but it's just a constant, I'm going to look it up in that map, and if I already have a label for that exact value, then I just return the existing label. So that means no matter how many times I type 1 plus 1 plus 1 plus 1 plus 1, I'm only going to store a single constant 1 in memory, and it's that every time I write 1, it's going to be reused at that existing location. So if we got a label, great. Otherwise, we need a new label, and we're going to remember it in the map and return that for whoever needs a label referring to a constant. If I need a label for a symbol, I have a separate map where I have names to labels. And if I look it up in that map and I have one, great, just return the label. Otherwise, I'm going to make a named label, and the name of the label will be the same as my symbol that I parsed out of the input text. And because of the way I wrote my grammar, all of my named values are valid symbol names because they begin with a letter, and then it's any number of letters, digits, and underscores after that. So I can use that name directly as the name of my label and store that, create a new label for that name, and stick that in the little lookup map. So let's take a look at what this looks like when we run it. Before we look at running it using the compiler class, so we're just looking at the assembler class. I'm going to go over here and, properties, debugging, and I'm giving it the command line argument to say, I'm going to type in my formula, I want you to assemble it, and then call the assembled function. So if I run this program, it needs a little bit of rebuilding since we were fiddling around the files. And then it says enter an expression. So I'm going to type, 1. The assembly that was generated said move a quad from the address pointed to by L0 into XMM0 and then return. And then in my data section, here's L0 and the quad word that was defined to hold that constant value. And then the program reported to me that it was evaluated to be the value of 1. So that's not particularly exciting. So let's run it again. And in this time, we'll give it, like pi times 4. And here we got in the data section, because pi was a predefined constant in my symbol table, I defined values for pi and for e. So here's the 64-bit value for the floating point value of pi. Here's the 64-bit value for the floating point value of 4.0. And it's going to load pi into XMM0. Then it's going to stash off XMM0 by transferring it the low 64 bits into RAX and then pushing RAX. Then it's going to load the other constant down here from label 1 into XMM0. And then it's going to move XMM0 into XMM1. Then it's going to pop the saved value back into RAX, move from RAX into XMM0, and then it can multiply XMM0 and XMM1 and return. And we get the value that we expected. And as you can might expect, if I do something, excuse me, if I could do something more complicated, like actually, let's do it this way. I have a little stash. If we go back over to my command prompt, this one. I paste this in. It went by a little fast there, so let's scroll back up. So it's a big bunch of parenthesized sub-expressions, and because it's parenthesized, it forces the order of evaluation to keep traversing down in my AST. So that's why you see it moves a constant into XMM0, and then it has to push, and then it loads. It's reusing the constant at least, but it's not smart enough. I didn't do any optimization on my AST to try to collapse any of this big constant expression down to something. But it's doing a bunch of this repeated stuff. Now it's only using XMM0. There's in 64-bit mode of SSE, there's actually more general purpose registers than just XMM0 and XMM1. You see, after I've pushed everything down, and then we start popping off, and now we're going into XMM0 and XMM1 and combining results back together, but there's still, there was all this stuff that we pushed onto the stack, and then we start popping it all off and adding it back in. We're only using 2 of the registers available to us. We've got more registers we could use. We're doing unnecessary communication with memory. Now, in a modern CPU, there's onboard on-chip cache, level 0 cache, level 1 cache, and so on. So this may not be slow, but we're still not really using all the registers that we could use. And that's where the compiler class comes in ASmJit. If we go back over here, look at their documentation, look at the compiler class, the main advantage that the compiler class gives us is that when we are emitting assembly language code, we can ask the compiler to allocate registers for us. And the compiler class will make registers available to us so long as they are available. And then when we run out of registers, it'll start using the stack. So if we run, just to see the difference, we go back over here and get to our little example program and change it from assemble to compile. And then we run this again, and now it wants an expression, and I say, 1 plus 2 times 3 minus 4. We can see that the assembly language emitted was move this constant into XMM0, move this other constant into XMM2, move this constant into XMM1. We still haven't exhausted our register set. Multiply 2 and 1 together. That's this multiply. The multiply has to happen first. Then add registers 0 and 2, and then move constant 5 into XMM1 and do a subtract. So it did the multiply, then it did the add, and then it did the subtract. The result was 3. That's what we expect because this is 6. Minus 4 is 2, plus 1 is 3. And we got 4 different constants stored in our data section. Now, if we take that nasty example and run again with that nasty example, we see that this is, I designed this example so that even when using the virtual register allocation with the compiler class, we would still exhaust the available register set and it would need to use the stack. And what we see here is that it adjusts the stack pointer by the amount of storage that it needs for these temporary values. We can't assume that the registers that are coming into us are available as scratch registers in the sense that we can just stuff whatever we want into there and it won't have any consequence for the code that is calling us. Again, that comes back to the ABI, what the calling convention is, what registers you're allowed to overwrite, what registers you need to preserve. In this code, it's saying, I need to preserve these registers before I can use them. So it reserves space on the stack for the registers we're going to save. It saves them onto the stack. So this is moving from a register to the memory address that is contained in RSP with an 8-0 offset. So it's saving all these registers on the stack. Then we're going to load some constants into the registers that we're going to use. And then we ran out of registers, so we have to save onto the stack a register before we can move into it. And that happens a couple of times in a row. And then finally, we start doing the add operations that are combining all these register values together. And once we've used up all the values that we have in the registers, then we need to start pulling some of the saved values that were stored onto the stack back into the registers and adding them in again until we finally have finished up the whole thing and we've got the result in XMM0 and we can exit. And down here is our data section, which only needed one constant because it was this input expression. It was just all ones. Right, so down here we've got our return value computed. Now we need to restore those saved register values and then adjust the stack pointer before we return, and then we can return. So here you can see that we're not doing any of this kind of manually pushing just to keep reusing XMM0. We're using as many registers as we can, and we're only pushing onto the stack when we've exhausted all those registers according to the register allocator in the compiler class. So let's look at really quickly how that looks different. At the top level, it looks pretty much the same. We need a code holder. We're going to init that code holder. Now we're going to create a compiler to associate with the code holder instead of an assembler. And we start the compiler by adding the function first. So this function signature build, this is where we have a function that returns a double, and there's no additional template arguments, so the function takes no input arguments. In terms of this build method, the return value is first, and then you have additional template arguments representing the types of the input arguments to the function. Our function doesn't take any input arguments, and it returns a double, so there's only one template parameter to this build method. And here you see I am allocating registers from the compiler. I say, give me an XMM register that I'm going to treat as a scalar double. So that's when I call this factory function, it builds me an XMM register, but the type of the register is annotated as I'm going to be using this register as, even though it's an XMM register that holds two doubles, I'm going to be treating this XMM register to hold a single scalar double. I'm going to recursively invoke compile on my AST, and then instead of emitting a ret instruction with no arguments, I'm telling the compiler that the register that corresponds to this result, I need it to emit the necessary code to have that register end up in the right place so that it is interpreted as the return value of my function. And then I'll end the function, emit the data section as before, call finalize on the compiler, and then I can ask the runtime for a function pointer from that code holder. When you call this comp.finalize, that's pretty much, you don't need the comp anymore. All the stuff's been written into the code holder. If we look at these compile methods, again, we'll look at the one for binary op because that's the one that's the most interesting. So we're going to pass the XMM register that we're using to hold our result. That's being passed into this compile method. We didn't do that for the assemble path because the assemble path was using the registers in a kind of just stupid way, which is always using XMM0. But we're going to compute the left-hand side into this result register. We're going to get a new register to store the result of the right-hand side. And then based on the operator, we're going to invoke the corresponding XMM scalar double function, or sorry, instruction. It's a method on the compiler to emit that instruction. And we're going to say, you know, the left-hand side is the result register, and the right-hand side is whatever this new register that was allocated to compute the right-hand side. And the reason we didn't allocate a new register for the left-hand side is because, you know, when we call these instructions, the source, one of the destination register is one of the source registers. It's always, you know, a modify in place kind of operation. So we know we need to compute the answer into this result register. So why don't we just use that as the first argument to these methods that do, you know, for instance, XMM0 equals XMM0 minus XMM1. I wrote 1 here, but, you know, it's really just whatever XMM register was allocated to hold the result of the right-hand side of this binary operator. And I don't think there's really anything different here because when we're doing, if you look at this code is like identical, except for the fact that in this one I'm calling a method on the compiler, And in this one, I'm calling a method on the assembler, and that's why these functions get constant label. That's why they have a template argument for the emitter, because the code is identical. It's just that sometimes the emitter is the assembler class, and sometimes the emitter is the compiler class. And really all I needed from that emitter was just, to get a label if I didn't have one already. So that is, a kind of a brief introduction. I mean, oh my gosh, we talked for like an hour and a half. So try to be brief, but there's lots of details in assembly language programming. The nice thing about AsmJit is this compiler class, I thought, that where we got, don't have it up anymore, so let's just run it again. And do I have that in my paste? No, of course not. So we have to go back here and clip it again and then paste it in here. The nice thing that I liked about that assembler class is that, it was using as many registers as possible without me having to worry about it. All I need to do was just say, hey, I need a register that's distinct from any register I'm using currently, and I need you to stick this value into it. And when I ran out of physical registers, it just started saving things on the stack for me, and it did all the necessary code to adjust the stack pointer before, the so-called prologue and epilogue code. This is making sure that when I call this function from C++, I'm not trashing any registers that I'm supposed to save, and making sure that when I return back from the function, that we're restoring those values. And in the middle, if I ran out of registers, it's used the stack temporarily to save things off and restore them as needed. So that, to me, saved me a lot of headache. It lets me focus on my algorithm instead of worrying about which register did I use. How many do I have left? Which registers have I used so far? Do I need another one? If I need another one, do I have room, or do I have to save something on the stack? The compiler class took care of all that for me. Now, sometimes, maybe you got a particularly fancy assembly language algorithm and you know exactly how many registers you're going to use, and it's all going to fit within the available register set, and you don't mind emitting the prologue and epilogue code yourself. It's fine. Use the assembler class if that's the way you want to do it. I found it easier myself to use the compiler class to generate, to have its register allocator handle all that stuff for me. Now, there's obviously a lot more you can do from assembly language in terms of there's ways, and this is all in the AsmJit documentation, so it's not like you have to figure it out yourself. You can call C functions from assembly language, and obviously through these function pointers, you can call the assembly language function from C functions or C++ functions. Again, when you're calling functions, you need to understand the ABI in terms of setting up the input parameters and interpreting the return value. AsmJit provides the machinery for calling a C function from assembly language, but it doesn't automatically handle the ABI. So just as we saw with the prologue that it created for the register usage, you have to do similar things of setting up the stack, setting up the registers before you call a function. And that is going to be compiler specific and platform specific and CPU specific. So combination of operating system, CPU architecture, compiler tool chain. Those three things together, you have to figure them out in terms of calling a function. So in my case, when, let's go back here, where we got here. If I were to fully implement this for my use case, I need to call these functions. Now, these functions, we're talking about not just cosine, but, or not just the sine function, but the sine of a complex value. So the sine of a complex value results in multiple calls to trig functions on doubles, scalar values, So if I were to implement this assign function in terms of assembly language, it wouldn't just be a straight call to the standard library assign function for a complex number. I'd have to, juggle some things around and do, figure out the math myself. But when I get to my full implementation, that's something I'm going to have to do, and I'm going to have to enhance my parser to understand the power operator and assignment. I just treated every identifier as a constant whose value was 0 if it hadn't been set to something. But in my little formula language, it's going to be a lot more complicated. I have to represent multiple statements in a sequence, and there is assignments and updating of variables and so on, and that represents values that I have to be storing into memory to represent the updated value of the variable and so on. So it's a little more involved for a full-blown example of what I need to do. But in terms of generating some assembly language and using the register allocator in the compiler, this is a pretty full-featured example. Now, when we ran it, I lost the window again. Okay, so we're going to have to run this really quick, and hopefully I still have it in the paste. Okay. When we ran it, we saw the assembly code that was generated. The reason we saw that is because I hooked up the logger on the code holder. If you don't do this, then you won't get this assembly language output. The logger that I'm using is the file logger from AsmJit. This is a logger that writes to a file star, and I'm associating it with the file star for standard out. There's a couple other logger classes. There's one for writing the output into a string. Like if you're in a GUI application, maybe you don't want it writing to standard out. You want it to go to a string so you can display that in a dialog, what have you. And if the existing loggers don't suit your needs, you can always implement your own. And as long as you implement the logger interface, if you look at that, here's the logger interface. As long as you implement this interface, then you can supply your own logger. You notice there's a bunch of methods in here that are concrete that you're not supposed to override, but there's this virtual _log method. That's the one that you would override to provide your own logging functionality. So if you need to do something custom, you can do that. Like perhaps you're doing this JIT compile inside an embedded environment, and you want your logger to write bytes over a serial port UART, and you don't have a file star associated with that. You can write your own logger and have it shuffle the bytes across the UART. I found the documentation to be quite good, and I didn't need to read. I kind of skimmed over everything. I didn't need to read the details of all the methods, although you can drill down that far if you want to. Like you can look at base compiler and drill into the implementation, look at all the different methods here if you need to, find out what a kreg is and so on. So documentation is complete. And if you get stuck or are confused about how something works, there is that chat window that you can go to. You can register there with your GitHub credentials and get information. Usually at least for me, this past week, the author of the library was there and was available to answer questions. Obviously, it's not people's full-time job to answer questions, so you may ask a question and not get an answer right away. Just be considerate of other people's free time. But so it's, to me, I thought this was a very nice library. I really liked the register allocation, and I think this is going to be what I'm going to end up using instead of LLVM because it's a very lightweight dependency, and it although it is very low level, I'm writing assembly language after all, I think it's going to be a good fit for my use case, and maybe it will be for yours as well. So that's all we got.